All right. Well, we'll start the lecture and we'll try to figure out what happens when we get to the point where I show this. How's everyone doing here? Alive. Excellent. Assignment tomorrow. Study guide to you by Friday. Last time we talked about and left kind of hanging what was the limits of what a Turing machine or our modern computers could do. We wanted an idea of what can't modern computers do. And to be able to answer that question, we need a couple of further definitions. And both computability and decidability. So we'll get into first the concept of computable. And in order for a problem to be computable, for that problem, we must be able to construct a Turing machine that computes some function for all arguments in the domain of that problem. If that is true, then this function is computable. So this is just about every algorithm you've ever written, where we're converting inputs into outputs. It says for every input in the domain, there exists one output. And that's the case in order for it to be a function. So any problem is computable if we can find such a function. If a problem is not computable or uncomputable, then we cannot find such a Turing machine. We can't find a function for which for every element of the domain there exists an element in the range. There is a function that maps the inputs to the outputs or does not map the inputs to the outputs. Decidable is when the output is yes or no. It's a binary output. So we restrict the output to yes or no. And then we ask, can we construct a Turing machine that answers yes or no for every possible input? If a Turing machine does exist for that, it can answer yes or no for every instance of the problem, then it is decidable. So we can link this concept of computable and decidable to the recursive languages, because recursive languages could answer both yes and no in a finite amount of time. For a given input, it will either answer yes or no. So this is basically the concept of a recursive language defined over either whether the output is binary, which means the question is decidable or not decidable or undecidable, or computable if we're trying to map inputs to outputs that are not just yes and no. So that's how we distinguish between the concepts of computability and decidability. We do have to make one note to this, that the domain of the function must be clear to be able to decide if it's computable or not. If we can't decide on what the domain is, then we can't conclude whether a problem is decidable or not. But there are quite a few interesting problems that turn out to be undecidable, something that a modern Turing machine can't answer both yes and no to. And the fundamental central problem to this is the halting problem. So let's define the halting problem, and then we are going to introduce why the halting problem is undecidable with a very fun proof that when presented kind of mathematically doesn't make a ton of sense, and when you're given a lot of visuals makes a lot more sense. And I'm just hoping that I can get some sound in here by the time that I couldn't get it working within 10 minutes before class, and that's worked on the first try every other time I've tried in this room. Gotta love technology. Anyway, the goal of the halting problem, you can imagine wanting to do this yourself, is to write a program to determine whether another program and an input are going to halt. So before thinking of this as a Turing machine problem, I'm going to phrase it to you as a programming problem. Imagine trying to write a Java program that takes as input another Java program and an input to that Java program. This program must simulate that input on that program and answer yes or no, will that Java program terminate or not on that input? So what that means is your program must work in general. You're not analyzing a particular program. You're writing a program that takes in an arbitrary program. And I think that's one of the main confusion points in the halting problem when people are presented to it. You're not given an algorithm and said, does this algorithm halt on this input? And then you get to analyze that particular algorithm yourself. You must do this in general, come up with a process, and that process must work for any possible program that it is given. Does that make sense? Or are there any questions on the concept of the halting problem? So you write a program, that program analyzes another program and an input to that other program to determine whether that other program terminates on that input or not. And if you can do this, you solve the halting problem. That is the halting problem. It is given an arbitrary program and an input, does that program terminate on that input? In terms of a Turing machine, we need a Turing machine program to determine whether the input pair of a Turing machine and a string, when we emulate the Turing machine on that string as input, does it terminate or does it go into an infinite loop? So yes, we need a single program to determine this for an arbitrary Turing machine program and string. So is it possible or impossible? I would argue that most people who have not seen this or had it introduced the way that I have so far introduced it would say that they think this is possible. And I've probably spoiled with everything that I've done leading up to this, that this is in fact not possible. Any intuition as to why this is not possible, or a counter argument where you want to put forth some logic that might say that this is possible? I want to hear your thought process on this problem. How do you see it? What do you think about it?
So, like, we know that there are recursively enumerable languages that never stop.
Right.
So naturally, if we know that about Turing machines, that means that there will be some that will never halt, or we can determine if they'll halt.
Right. So we need the ability to determine, though, whether it could halt. You can imagine looking at a Java program and seeing a while true, and there's no break inside of it, and there's no system exit. Could you, with the syntax of a particular program or a loop, could you figure out, yes, of course this program is never going to halt? Could you look at a particular loop, going through a for loop and saying, well, the termination condition is this number, but the for loop is decrementing and we're getting farther and farther away from this. Of course, we're never going to get back to this high number and eventually terminate. The arguments I've heard in the past involve something like that, or involve looking at the syntax and being able to say, well, I could look at the syntax of a program. I could say that the program is my brain. And when I look at the brain of a Java program, I could look through and determine whether this loop would terminate or not, given enough time and knowledge of logic. So why wouldn't another program be able to exist that could do this in general? Anyone else have any thoughts on that? This is kind of a deep question, which is why I'm giving you a little bit of time to think about it. It's not, you're not going to have a straightforward answer that pops to the front of your mind immediately. My view on that is that you could do this for specific types of loops within particular kinds of syntax. If loops are created in such a way, then you may be able to, in general, determine whether a loop would terminate. But there are so many different kinds of loops and parameters and arbitrary functions and arbitrary updates to those functions that could you really determine for an arbitrary loop whether it would terminate or not? Thinking of everything that is within the power of a loop. Any initialization condition, any termination condition, anything mathematical, any update function. Let's see if we can come up with an intuition via this proof by contradiction of why this is not possible. So, proof by contradiction, as is every proof in this class, we're going to start by assuming that such a Turing machine exists. We're going to call it H. This Turing machine solves the halting problem. It will end in some final state if M accepts W, and in another final state, we can halt and reject if M does not accept W. One way to visualize this is, here is the Turing machine, starting in an initial state. We're going to say the machine, when given string W, is going to either accept or reject. So we are going to use that as our initial state. We're going to emulate what happens on that machine. And we will end in Qy if M accepts W, and Qn if M does not accept W. All right, we're going to make a small change to H. All right, if we reach Qy where M accepts W, rather than halting, we're just going to enter an arbitrary infinite loop. Because we can. Do we agree that that's something we could do? Rather than halt and accept, we're just going to force an infinite loop there. And that's the only change we're going to make. So this is H loop, where we feed M W, and if M accepts W, we're going to enter an infinite loop. And if M does not accept W, we will halt and output that M does not accept W. We agree this is a Turing machine we could make? The legal Turing machine? All right. We're going to construct a third Turing machine that we call H proof. This is going to be what creates the contradiction. So this machine, H proof, it's going to take M, which was the original Turing machine that answers yes or no. As M, that's the binary encoding of the input to H as input, copying it so that it's also the string. This basically says that what we're doing is we're going to feed this H loop into H proof as both the machine and the string as its input, which is a really strange idea, but this ends up working really strangely. So after we do this, it behaves exactly like H loop. So we're feeding the concept of H loop into H proof with the goal of, as it does this, it's going to either accept that H loop halts and accepts H loop as the string, or doesn't. So, yeah, we also as string feed itself. So we encode this Turing machine in binary as a string that we're going to call W proof. So we now feed W proof into H proof. So it takes itself and itself as a machine in string form as both the machine and the string. And if we do this, we see that H proof halts on W proof if and only if H proof does not halt on W proof. And H proof does not halt on W proof if and only if H proof halts on W proof. And I feel like I never do this justice, which is why I want to have a video that actually explains this. Because all that we've done is we're taking this idea of if the answer is yes, then we go into an infinite loop. And if the answer is no, we can answer that. Now, what we do when we take this idea and we feed it into a Turing machine, that we take this machine and a string that looks like this, and we feed it into the machine. The idea is if we can answer yes and no to the halting problem, then what happens when this machine takes itself as input? If the answer is yes, we halt, which would answer the halting problem, we go into an infinite loop. And if the answer is no, we don't halt, then we halt. Because this infinite loop exists, the answer is, does this machine halt on its own input? If the answer is yes, it halts on its own input, then it goes into an infinite loop, which is a contradiction. If the answer is no, it doesn't halt on its own input, then it halts and tells us no, it doesn't halt on its own input. Regardless of what we do, it's wrong. It's wrong about what happens when it runs on itself. And that's what creates the contradiction.
Why is it important that it runs on itself as a string? Like, why is that important?
Because it has to answer its own question about, there's no other way. If we ran it on something else, then we'd be able to say, like, that's a good question. How do I want to explain this? In order to run on itself, the only thing that's dependent on this infinite loop structure is its own construction. So it would be something like, I need to determine whether or not I need sleep. That's kind of like an infinite loop, right? If I can go into an infinite loop, if I can stay awake forever. And if I run out of energy and terminate, then I would fall asleep. So in order to make a contradiction, I would need to run this on my own algorithm. I couldn't use someone else's algorithm to determine whether I need sleep. I would need to run that on my own process. And so the idea here is, I'm going to answer yes, I need sleep, or no, I don't need sleep. And this construction that we've made legally says, yes, if I need sleep, then stay awake forever. And no, I don't need sleep, then fall asleep. And if I have the ability to construct this in such a way that if I conclude that I need sleep, I have the ability to stay awake forever, then that contradicts the idea that I need sleep. Because I indented this concept of this part of this that says stay awake forever to the end of that process. I don't know how well that worked, but
No, I understand.
yeah.
In H loop, why is QY no longer an acceptance state?
Because it goes directly into that infinite loop. So a final state in this case designates that it halts. So we're keeping this acceptance from halt by going into an infinite loop. If we made that a final state, then it would halt at that point and not go into that infinite loop.
But that seems like it should be invalid in that sense, because it no longer seems to answer what the original H represented is, one with a final state QY and a final state QN.
Yeah, so we would be able to say, yes, that it does that, but by doing this with a construct, we're saying that rather than terminate at that point, we're just going to addend to the concept of an infinite loop, which means that we don't halt. A final state in this machine means we have to halt. So yes, we could say that we're going to halt at this point, but it is a legal construction. This is a machine that could be made. Since it is a legal machine that could be made, it is a machine that we could use as input And any machine that solves the halting problem would have to be able to solve the halting problem for this addended machine as well, because it has legal rules as something that we could do. It is a constructed Turing machine, a legally constructed Turing machine. So any machine that solves the halting problem has to solve the halting machine problem for this machine as well.
But in the same way that you can see that by staying awake for too long, you have detrimental health effects, determining that you do in fact need sleep. It wouldn't a Turing machine that can analyze Turing machines see that this goes into an infinite loop and determine that that doesn't halt, that doesn't halt?
Not necessarily. So if we were able to do this, then we would need to be able to determine and be able to answer yes and terminate that this goes into an infinite loop. The idea would be if we could answer yes, this could terminate and go into an infinite loop, then construct a different infinite loop, something that's more complicated, that it couldn't say goes into an infinite loop. There's no way, based on this machine, to determine that it's going into an infinite. So basically, that is the proof that Turing used in his thesis, is that any general solution to the halting problem would need to solve the halting problem for this machine when fed itself as input. So the machine that solves the halting problem is going to need to be able to take in the machine and the string that represents itself and answer, does this halt, yes or no? But regardless of what it answers, it's wrong. If it answers yes, this program halts, then it immediately goes into an infinite loop and doesn't halt and can't answer yes. And if the answer is no, well, it's going to go into an infinite loop. Then it halts and tells you that it's going to go into an infinite loop. So what I really want to do is get this up and running. And it doesn't seem like I'm going to be able to do that. So, all right, so the video didn't quite work. We're watching that between today and tomorrow. But once we see the full halting problem and its grander scope, one interesting conclusion from that is that if the halting problem were decidable, then every recursively enumerable language would also be recursive, which is a very interesting conclusion to see as well, because we could end up taking any recursively enumerable language, turning it into the halting problem. The halting problem is decidable, so now that language is decidable. And that brings us to a new proof type that we're not going to go through in this class in more detail than just introducing you to it, but it is very interesting to see how to prove something is undecidable. So I guess first, who remembers NP-complete proofs or NP-complete reductions from algorithms? Is that something we went over?
Probably so. Maybe.
All right, we'll start with what was NP-complete?
Had to do something with the time complexity, right?
Yes. All right, we'll start with what NP-complete was. So an NP-complete problem is one that is in a set of problems that is proven to be basically the best that we know with regards to a deterministic solution has an exponential time complexity. However, if we allow for full non-determinism, there is a solution that exists in polynomial time. So NP stands for non-deterministically polynomial. And NP-complete is a series of algorithms that if we had a graph, we could show that there are polynomial time conversion algorithms between these problems. So we have some problem we know to be NP-complete. have I done this in this class? I never know what I've done in this class, but yeah, this is starting to sound familiar. It's probably something that we did a while ago, but you start with something like the traveling salesman problem that we know to be NP complete, and we can find another problem like the SAT problem that we're curious about the complexity of this problem, and we can't determine whether it is solvable in polynomial time. We can't solve it in polynomial time, but we can come up with a conversion algorithm between this and that is polynomial. The idea would be that if we could solve this in polynomial time, then we could solve this in polynomial time, convert it in polynomial time to this problem, and then we could also solve this problem in polynomial time. So NP complete is this large graph web of problems that none of which we can solve in polynomial time deterministically, all of which we can solve in polynomial time non-deterministically. And if we could solve any one of these problems in polynomial time, then we could solve all of them in polynomial time via the proofs that connect all of these problems in polynomial time. So that's the concept of NP complete. And it turns out that that is exactly what we have with regards to decidability as well. We know that the halting problem is undecidable. If we come up with a problem and we determine, is it decidable? And we can't answer that question one way or the other, then we could do something like, can I come up with a proof that says, if I could solve this problem, then I could solve the halting problem. You try to convert this problem into the halting problem in some capacity where decisions in this problem are mapped onto decisions in the halting problem. And if we can do that, then we can come up with, we know for sure that since the halting problem is undecidable, if this were decidable, then the halting problem is decidable. We know from discrete math, if P, then Q. If we know not Q, in that case, we can determine not P. We can conclude not P. So similarly, we can conclude that this new problem is undecidable. So undecidable problem reductions utilize exactly that logical step. So it's a connection between one undecidable problem and another. We'll start with just the halting problem, but as we start seeing more and more problems, we start to add more problems to this undecidability web, where if we could solve one of these problems, we could decide one of them, then we could decide another problem. And if we could decide that problem, then we could decide another problem. And if we could decide that problem, then we could decide the halting problem. And since we can't decide the halting problem, we can add it to this web of problems that are undecidable. There's no other way to prove that something is undecidable. We can't just show that, because if it's undecidable, then for some inputs, it spins forever. And it's ambiguous as to whether it will eventually halt or not. So the only way to add something to this class of undecidable algorithms is to theoretically link it to a known undecidable problem, or to prove kind of the way that the halting problem was proven to be undecidable, with some outside logic that doesn't involve running the inputs like that. So yeah, problem's decidability can be determined from a known undecidable problem. Then the query problem must also be undecidable. If it were decidable, we'd have an algorithm to decide the undecidable problem, which we know can't exist. So as we discover more and more undecidable problems, then we end up with more possible places, more possible ending points for our proofs. We don't have to decide and link something to the halting problem. We can link it to any other known undecidable problem. Very much like for NP-complete problems, the more NP-complete problems we have, the more options we have for finding a polynomial time conversion algorithm between the query problem and some other problem that we know to be NP-complete. When there are 10 known NP-complete problems, there are 10 possible endpoints. When there are 1,000 known NP-complete problems, there are 1,000 possible endpoints. And these problems look very different in nature. So it might be easier to link something to one of those problems than another. It is very much that case. Let's give you an example of this. So we want to determine the decidability of whether a Turing machine enters a particular internal state when M is applied to an input string. So we make some Turing machine, we give it some string, and we want to always be able to determine. So this would be, we want to make a Turing machine that can take another Turing machine and a string, and an internal state of that Turing machine, and answer the question is, as we run this machine on that string, does that machine enter the query state? If the answer is yes, output yes. If the answer is no, output no. What do we think? Is that possible? From the context, we know the answer is no, but intuitively, why? Yeah,
Just based on the previous slide, it's gonna seem like you can't do it because we can't solve whole.
yeah, we're definitely going to reduce it to that.
Yeah.
Intuitively, imagine that this Turing machine loops forever on this input. And getting to that loop and iterating that loop once does not enter that state. Who's to say? It's ambiguous at this point. This loop has been going on 10,000 times. Whether this loop is going to terminate and eventually get to that state on its way to acceptance. Or is it going to spin forever in this loop that it's been going through 10,000 times? It's ambiguous. We don't know for sure unless we can determine that this is spinning forever. So we can reduce this to the halting problem in a way that says, if we could solve this problem, then we can solve the halting problem. So we call this the state entry problem. Proof by contradiction, we say assume there exists an algorithm that solves the state entry problem. We'll modify that machine, M, the M that we're using to query this, to get M proof from the halting problem in such a way that M proof halts in state Q if and only if M halts. The idea being that whatever state we halted in, we're going to change from being a halt state and we're going to redirect it to the query state and saying instead of halting in the halt state, we're going to halt in the query state. We then just apply the state entry algorithm to that machine with the string, with the query state Q, and now this is the equivalent of the halting problem. If we halt, then we get to the query state. If we don't halt, then we don't get to the query state. So we've reduced it to the halting problem with the idea of if we could solve this problem, then we just manipulate it in such a way that we get the halting problem, and we can solve the halting problem with the state entry problem. So if M proof answers yes, state Q is entered, then M proof halts. If M proof answers no, state Q is not entered, then M proof does not halt. And we have the halting problem. So we've now solved the halting problem. The state entry problem was decidable if and only if the halting problem was decidable. Since the halting problem is undecidable, the state entry problem must also be undecidable. We have P implies Q and not Q. Those are the two things that we know. We can conclude not P. Questions on that? There are tons of other fun, undecidable problems. When we look at recursively enumerable languages, we start getting very handicapped in terms of what we can answer and not answer. There's not much of interest we can say about recursively enumerable languages, and there's even less interesting that we can say about non-recursively enumerable languages. There's just next to nothing we can know about. But even for recursively enumerable languages, there's not much. So no membership algorithm for recursively enumerable languages, because an algorithm must terminate, and a membership algorithm won't necessarily terminate. So very little of interest can be stated. A lot of the simple questions that we could ask are undecidable. So here are some examples. Assume that we have an unrestricted grammar and we saw a couple days ago that unrestricted grammars were equivalent to recursively enumerable languages. Is the language described by the grammar empty? Does it contain zero strings? This is undecidable. Let's say that we have a grammar, and in 10,000 derivation steps, we've looked one step away from the start non-terminal, 2 steps away from the start non-terminal, 3 steps away from the start non-terminal. After a very long time of doing this, so far, we have found 0 strings in the language. Does that mean that the language is empty? There are no strings that are in the language? Not necessarily. I could construct an unrestricted grammar that, as far as you've looked, I could make the first string appear one step beyond that. I could construct such a grammar that targets exactly that. So because of that, it would be ambiguous, regardless of how far you've gotten in that process. You can't terminate and say there are no strings in this grammar. So it's undecidable. Let's assume we have a Turing machine. Is the language accepted by that Turing machine finite? This is also undecidable. Can reduce this to the halting problem. But the intuitive idea is this has been going for quite some time. You've been adding strings to this language. Just because you've added some number of strings, some large number of strings to this language, does that mean you're not going to ever stop adding strings to this language? We don't know. It's going to be ambiguous. I could make a very large finite language that, as far as this process has gone, one step further is the last string. And then it terminates. And every string has been added to the language. So we have a Turing machine over an input alphabet AB. Are there 2 strings in the language accepted by that machine that are the same length? When we find 2 strings that are the same length, we halt and say yes. If we have gone for a very long time and haven't found 2 strings that are the same length, can we stop and assume that that will never happen? No, it's ambiguous. I could construct such a Turing machine that takes a very, 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 very long time to collapse on itself and produce a second string of the same language, of the same length as something that we saw before. That would be possible for me to do, so therefore it is ambiguous. Also undecidable. Also a reduction to the halting problem. It may seem like these reductions are kind of an abstract idea, not particularly useful in the day-to-day. So halting problem is kind of cumbersome to work with, if that makes sense. But it turns out that a lot of conclusions that we can make about even the language classes that we've covered so far in the class follow the concepts of these reductions. So it's worth looking at some of the problems that are actually middle grounds for coming up with these important conclusions about some of these languages that we've seen before. And I will, with the very little amount of time we have left, introduce the post-correspondence problem. So the post-correspondence problem says we have 2 sequences of n strings over an input alphabet. There's a post-correspondence solution if there's an arrangement of the sets of strings that produce the same output string. Here's an example. The string is 111001111, and we want to determine whether, when we have W, which is the subset 11, and another subset 100, and another subset 111, and V, which is the subset 111 and 001 and 11, whether there are ways to tile with W and with V in such a way that you get the same string. It may seem that you would just go through every single combination of W and V. And if there is such a way that does this, then you would have it. And otherwise, no. It turns out that this is not decidable for every possible string set. it would be decidable for this particular problem. But as this scales, as we look at different string sets, it turns out that this is undecidable. If there is such a tiling, we will find it. If there is no such tiling, we'll spin forever. So we can make a modified post-correspondence problem with setting the initial strings, W1 and V1, that have to start this particular set. So W1 must be in the first position, locked to the first position. V1 is locked to the first position as well. And then this becomes the ability for us to start in different derivations of grammars where we have kind of S1 and S2 for two different derivations of the same string. And that becomes very interesting with regards to how we can determine the parsing problems within context-free languages. And we'll come back and start talking about that tomorrow, but we'll do it after talking about the video. So I'm gonna go post the link to the video. It's 33 minutes long, not the world's longest video. Please watch it before tomorrow's class so that we can have a discussion about it. The discussion will only be as good as the number of people who have watched the video. So 33 minutes.